Good morning, good afternoon, and good evening to all our viewers globally, and welcome to this webinar brought to you by IMarEST Houston. It is our privilege to host another webinar from Pratexo entitled Improve Industrial Resilience Using Generative AI on the Edge. Our speaker, Blaine Mathieu, will address the challenges and provides the latest advance on how generative AI can be used on the edge to accelerate the design, deployment, and management of such systems while ensuring they continue to run in the harshest conditions and environments. Blaine is a former software company founder, Gartner analyst, multi-time C-level executive at both public tech giants, private enterprise software, and industrial IoT startups. He is currently CEO at edge-to-cloud platform company Pratexo. For our global viewers, please note, this webinar is a listen mode only. So kindly use the Q&A chat box in Slido provided to you on the email you receive on the invite to send your questions, which will be addressed by the speaker at the end of this presentation. Without further ado, I invite Blaine to take it away.
Thank you. Thank you, Dr. Nimi Abili, and thank you to IMarEST for giving me the chance to speak today. Why don't we jump right in with that great introduction? I will share my slides, or share my full screen, in fact, because we're going to do some interesting things today. Here we go. So as Dr. Abili said, we're going to talk about industrial resiliency. And I thought since this is IMarEST, I would do my best to make the discussion even more specific to marine and maritime systems that I think most of this audience is quite directed into. I will talk more about Pratexo and how my company fits into this more toward the end of the presentation. But let's just jump right in. So, you all know, you're all probably more experts than I am on the maritime and marine space, but as you know, there's a lot of transformation going right now, a lot of new applications coming in related to, ship safety and security, of course, understanding the status of cargo. Maintenance and operations, of course, is really critical, and then ensuring the operational effectiveness of overall systems. And we're probably going to mostly focus on maintenance and operations today, although certainly the general topic we're covering applies to all of these areas. One thing we have learned over the years, and it's probably more relevant in the maritime industry than almost any other industrial sector, is the required capability to run these applications, these systems, these operational systems on the so-called edge, in this case, on the ship edge, because you cannot guarantee an always-on, high-speed, permanent connection to a central cloud. So you need to be able to do all these things, which might otherwise often be done with a pure cloud-based application, but they need to be able to operate and continue to operate even if disconnected from central clouds. That's what my former Gartner colleagues call edge computing, the ability to bring the analytics and algorithms down to the data instead of pushing all the data up to the analytics and algorithms. And so that's, I think, really critical, sort of foundational element to a lot of what we're talking about today. But what I really want to focus on, and the title of the presentation here is really related to system resilience. And I love this Gartner graphic for explaining a way to think about resilience. Obviously, in the face of potentially disruptive events, a machine shutdown, some kind of external stimulus, you need the ability to absorb, adapt, recover, and especially anticipate. That would be great. So not just to react when something happens, but anticipate to a problem, situation, or challenge happening. And then, of course, do something about it, take an action, mitigate. If you're not able to prevent it from happening in the first place, then at least mitigate the issue that comes up. And so the rest of our discussion is going to be focused on system resilience. And as I said, particularly using generative AI technology to enable this. The foundation of what I'm going to show here and actually attempt to give you a live demonstration of is some work we did with ABB really back in 2022. Pratexo won their ABB Startup Challenge back in 2022. And the foundational application or system we created with ABB was a root cause analysis expert system. The idea was, could you ingest data coming off machines and systems, industrial machines and systems, obviously, and then either in forensic mode, retrospective mode, or in real-time streaming mode, try to understand what's going on in these systems, identify the actual root cause of issues that might happen, and predict, of course, what might happen as well. This is the fundamental elements of system resiliency. And so we did work on such a system with ABB over the course of a year, in fact. And there's a QR code that links you to a few different elements, the ABB review article where they went into this system in quite some detail, and a few other things. If you can't catch that right now, I'll post this QR link at the end. So very interesting project and interesting concept. And let me give you an example of what a root cause analysis or what a fault cause analysis graph might look like. So think about it as a machine or system expert, in this case, an expert on, you can see at the bottom, main propulsion systems for a tanker, might want to understand potential faults for this main propulsion system. What are the things that could go wrong that you'd probably want to prevent from going wrong? What could be the causes of those faults? What are the indicators, or what things would you have to watch for? What analytics would you have to run in order to detect one of those causes either happening or about to happen? And then finally, what sensors would you use to push data into those indicators? Right now, again, I actually created this graph about an hour before the presentation today, and I am personally not an expert on propulsion systems for tankers. So I'm sure the experts on this call are looking at this and going, "Well, that's not quite right." But I hope you'd agree it's at least sort of directionally correct in terms of an analysis of what faults you might want to trap for, predict, or prevent, or at least address, and then how that would flow all the way to the data coming off the machines and systems and sensors. So this is the notion of a fault cause graph, and we're gonna hit on this repeatedly for the rest of the discussion today. So what we did with ABB was we said, okay, what if we had a machine or a system expert that sort of had in their brain, and maybe as well as all the documentation, service manuals, maintenance manuals, all the required systems that domain expert has at his or her disposal. Imagine if we could take all that knowledge and actually turn it into an application, convert it to computer code, convert it to a set of rules written algorithmically, create that fault cause graph and tell a computer how that graph flowed and how it worked, write all the analytics and algorithms that would automatically take the data flowing off those sensors and convert it into something that the fault cause graph and the rules could use, package all that up, turn it into an expert system that could ingest data and then allow you to take the right action, either proactively or in the case of something already happening, to take an action to address it or ameliorate it. This was the concept, the fundamental concept behind the root cause analysis expert system that we began to work on with ABB. What we found out, though, is there's a big barrier, my big red line here, between how you take the machine or system expertise of a domain expert and actually convert that into code. That's a hard thing to do because domain experts are not computer scientists. They're not big data analysts. They're people who know how to operate and maintain a system or a machine, an engine, whatever the case is, on a ship or in some other industrial system. And so to make this system actually run required a tremendous amount of work on the side of computer scientists and data analysts to listen and understand what the domain expert was saying, to get their knowledge base and convert it into computer code. This is a big, big challenge, as you can probably imagine. Then in early 2023, something interesting happened, and we've all experienced it, and that's the beginning of the so-called generative AI revolution, the idea of using AI in a way it hadn't been used before. And so in early 2023, just over a year ago now, the basic infrastructure began to be released publicly. It had actually been building for a number of years, but they released it publicly. And in particular, they released access to highly trained machine learning models. And these models, in fact, incorporated into them, and to this day still do, most of the, if not all of the sort of publicly available knowledge that's on the internet today. Now, you might think that includes a lot of Facebook posts and various things, which of course it does. But in fact, if you were to just focus on industrial systems and infrastructure, you can actually get access publicly to most of the service and support, maintenance manuals, product specs for the vast majority of industrial machinery systems, motors, engines that are out there today. And trust me, these generative AI models called large language models have ingested all of this information, right? It's quite incredible to think about. So with that as the foundation, we said, okay, let's take another look at this expert system concept. Could we actually create a tool or a platform or a builder that was able to use all this model data that had trained this artificial brain, all these brains, and use that to rapidly create this predictive maintenance application, this root cause analysis expert system we were just talking about? And in fact, we realized we could do that. As my, again, former Gartner colleagues say, the use of models to collaborate with and interact with knowledge workers, and I think that absolutely will include machine and system experts, is going to go up dramatically in the next few years. And so we thought, okay, let's revisit this project that we worked on and see if we could, superpower it with generative AI. So in this case, instead of having to insert a team of data scientists and computer programmers between the domain expert, the person who's an expert on marine propulsion systems, for example, and keeping that system running on a ship, instead of having to insert all those people there, we could use generative AI as a kind of co-pilot for that expert. And by bringing that system expert together along with that AI co-pilot, we could rapidly create the graph that we showed, the rules, deploy the analytics, package it all up in a way which then could be turned into an actual running system for predictive maintenance, analytics, and really understanding what's going on in your system. We said, wow, AI could replace a lot of that hard work that we thought was a challenge. Let's take it another way. So that led to actually a couple of weeks ago at Distributech, one of North America's largest energy infrastructure events, we announced a new version of our root cause analysis expert system that now replaces all those programmers and big data scientists with generative AI to enable the ability to design and deploy an expert system. And what I'm going to do right now is give you a live demo of this actually running right now. So of course, live demos are always fun on these events. The demo gods, you sometimes have a way of interfering. If all else fails, I did record a video of some of what I did earlier this morning just before the event. But let's go and give it a shot here. So I'm going to switch to my web browser. So this is now a live browser application. And let's go actually to the beginning. So what we're doing, again, is imagine you are a machine or a system expert. And in this case, we're going to use a maritime example, even though, again, I'm not an expert in these systems. The AI is a lot more expert than I am. And so it'll assist me in at least creating the basics of an application for predictive maintenance and fault cause analytics for a maritime system here. And so remember, what we're fundamentally working to do is to identify the faults that we want to trap or prevent from happening. This is part of our overall theme of resiliency. What could the causes of those faults be? What indicators would we have to measure in order to know this was happening? What sensors would drive those indicators would be necessary to have in place? What sensor and sensor data? And then finally, the ability to make predictions, to understand what's happening, and then also to take action. The action is actually a very important component. The goal of such a system, of course, is not just to have nice graphs and charts and blinking alerts. It's to actually have something happen in the real world. So let's actually build one of these systems right now from scratch. So first thing you have to do is give our AI copilot some context, all right? You have to tell it what kind of system, what kind of machine, what are we trying to improve the resiliency for today? So let's do that right now. Main propulsion system on a tanker. Okay. So I'll enter that in. Now I've just told the AI copilot here, this is the domain that we're interested in. As you can see from this screen, that you have the ability to provide a lot of additional information or context. You could even drag and drop maintenance documentation in here. But it's actually quite amazing what you can produce with just that little amount of prompting. And again, the reason for that is the AI model already has a lot of that contextual information in its brain, as long as you aim it in the right direction. So again, based on main propulsion system on a tanker, we're going to ask it to create a sample fault cause graph. And the purpose of this, again, is really just to see if our copilot here is working in the right direction. Give it a second. Okay, there we go. So let me zoom that in a tad. Okay, so here's a fault cause graph. Now this looks similar to the one I showed on the slide before because I used the same prompt when I did it this morning, but I won't show them side by side, but I do want to point out that this is not identical to the graph that I was showing earlier in the slide deck. The reason is that, of course, if you ask two experts, maybe on 2 different days, to come up with an analysis of potential faults in a complex system like this, of course, they're not going to come up with exactly the same system of flows and faults every single time. It's going to be somewhat different every time you do it, directionally similar, but not identical. And I can guarantee this chart is not identical to the one I showed in the slide earlier. But the concept is similar. What are potential faults that somebody who's trying to ensure the efficient, resilient operation of a main propulsion system would probably care about? What could be the causes of some of those faults? And you can see one fault might have multiple causes. Some causes could contribute to multiple faults. So this is not a pure one-to-one flow that we're seeing here. What could be a potential indicator of one of these causes? And again, it's showing a one-to-one relationship, but it doesn't have to be. It could be one-to-many. And then finally, what sensors would you need to actually push data into that indicator or that algorithm? So the purpose of what this has done so far, and I think hopefully the first time I saw this, I was pretty amazed that we could get this far with a very small a bit of information about the system. It could be something as specific as a particular type of machine or an integrated system like the one we're looking at right now. Pretty small amount of information, but what we've got, all we're doing right now is just making sure our assistant here its mind is thinking in the right direction. Because now what we're going to do is enable a human-machine collaboration between the person who's in charge of ensuring the effective operation of this propulsion system and the AI expert, so they can create the actual fault cause graph that the operator or the maintenance person cares about. And including the faults they really care about, the sensors they actually have access to. We're going to specify all that in collaboration with the AI right now. Now, to actually build out a complete fault cause graph for a system this complex, I imagine might take a day or two of concerted work. We're going to do something much more compressed here. But let's dive in, because I want you to get the essence of how that collaboration between generative AI and a machine expert would actually work. So first, we're going to identify faults, the first column in the chart. And of course, the expert has the ability to manually enter in faults that she wants to be able to trap for or predict. But we could also ask the AI to suggest some potential faults. Let's give it a second. Okay, so let's see, engine. Let's choose engine overheating. Oil leak might be one. How about transmission failure? That's a good one. So let's pick those. We'll accept those through the AI suggestion, and it gives a little further description of what each of these means. I want to enter in a couple as well. Low oil, just to show we can do this manually, if I can type. And let's see. Oil pressure is too low for effective operation of the engine. Well, that wasn't too good. I had too much background noise. Okay. Effective operation. Okay, good. Let's enter that one in, commit that change. Okay, so let's go to our graph now as we're starting to build it out. And you can see we've got four faults that we care about. Now, an actual operator or maintenance person who's trying to make sure this system is maintained and predicted may decide to focus on just one fault or a small class of faults and build a special application just for that. Or you may decide to, specify a much larger number of faults. It's really up to you how, if you want to run one integrated expert system that's looking at everything, or if you wanted to run a number of modularized systems, totally up to you. There are pros and cons to each different approach. We'll obviously do something sort of in the middle here. So now that we've identified a set of faults, let's look at what the potential causes of each of those faults could be. So now again, let's choose engine overheating to start with. We could enter in manually our ideas for what causes of engine overheating could be. But again, let's ask AI to come up with a list. That'll be help us brainstorm, and also just for demo purposes, it goes a lot faster. So remember again, the fault here is engine overheating. What could cause it? Insufficient cooling levels. I like that one. Clogged or dirty cooling system, malfunctioning thermostat, and a faulty water pump. Why don't we go with those as the ones we're going to accept? And let's do one more. Let's talk about low oil pressure. And we'll just ask AI to give us suggestions for what could be the causes for low oil pressure. Clogged oil filter, yeah, that's probably it. Faulty oil pump, insufficient oil level, and leaky seals. All right, let's go with all of those, accept those. All right, so back to our graph. So now what we've got is a few faults we've identified. For a couple of the faults, we didn't do them all, but for a couple of the faults, we identified what some potential causes of those faults could be. So the next step is to figure out what would be the indicators, what would indicate that one of these things was actually happening. All right, so let's go into indicators. So as you saw earlier, we now have 8 known causes that we're looking to trap. What would be an indicator of an insufficient cooling system? Again, it could enter manually, but let's ask AI to help us. So we might know that there was a insufficient cooling system by, some of these are sort of obvious. A malfunction of the cooling system, that makes sense. The next step is going to be to specify the sensors that would tell us there was a malfunction of the cooling system. So don't ignore the obvious just because it sounds obvious. You actually also monitoring engine temperature would probably be a good indicator of an insufficient cooling system. So let's choose those, and let's do oil, something oil related here as well. How about insufficient oil level? Okay, what would be an indicator of insufficient oil level? Maybe this one will be more interesting. Faulty oil pump. Okay, let's go in. Again, as you can see, this isn't, none of this is canned, right? I literally do not know what's going to come out the other end when I press the button. An expert on one of these systems, like most of you on the call, would probably know very well. Definitely faulty oil pump. An indicator would be being able to measure for an oil leak, low oil pressure, and engine noise. Okay, I'll just accept that. Again, I'm sure you would do a much better job of collaborating with the AI than I'm doing, but let's accept those suggestions. Now let's take a look at our graph, and you can see how we're starting to build it out. So some faults, we identified a few causes for a few of the faults, and then for a couple of the causes, we started to figure out what the indicators would be that would tell us that one of those things was actually happening. And to keep the graph simple, I'm not overlapping these things too much, but you could have an indicator that actually is an indicator of 3 different causes, right? It doesn't have to be a one-to-one relationship like we're showing right now. The next step would be to figure out, okay, if these are the indicators that I care about, the engine temperature, low oil pressure, what would be the sensors that I would need to actually provide that data to our application we're literally building right now in real time? I just want to focus on that point a little more. We're not just creating a pretty graph here. right? What we are literally doing is creating an application to be able to detect and predict these faults in the first place. All right, very important to keep in the back of our minds. So let's go into sensors. Two ways we can get at this, actually. We can either say, okay, if these are the indicators I care about, tell me what sensors we should use. Or we could say, these are the sensors I have already, and you could specify, and you could combine those things together, okay? Either tell it what you've already got and see how it fits, or you can have it suggest to you what the right sensors might be. I'm going to use the AI help part here just to make things go a little bit faster, since I don't want to be typing or selecting sensor types here. So for low oil pressure, what might be some sensor types we could use to detect that? Okay, well, and probably an oil pressure sensor and maybe let's see, and a pressure transducer. Let's go with that. We're going to have two different kinds of sensors to make sure we have backup redundancy over our oil pressure, such a critical thing for us. And what about engine noise? What would we use to indicate or detect? Well, actually, let's do cooling system. I like that. So what would be a sensor, or maybe a couple of sensor types we'd use to detect cooling system? Definitely probably some kind of flow sensor to see how much volume of coolant was flowing through the cooling system. Obviously, a temperature sensor on the cooling system, and maybe your setup has a few different kinds of sensors. Again, if they don't appear on the list, you can enter all of these things in manually as well. So let's accept those suggestions. Let's go back to our graph, see how we're doing here. Okay. So now we've built out a couple of the sensors that are going to drive the indicators. Now the next step will be to build out the predictions. So what would we want to be able to predict based on these indicators? And then what actions do we want to tell our evolving application here to take if one of those predictions is actually made? And it would probably take me another half hour to build this out. I did this just before the meeting. It took me about an hour. What I'll do to save a bit of time is I'm just going to skip ahead a little bit, and I'll show you how I did it when I did it earlier this morning. So here's the same context, main propulsion system on a tanker. I've just switched to a different tab here in my browser. Let me show you the graph. So this graph is a little bit different because I didn't do it identical to the one I did this morning. I identified a number of faults, still had low oil pressure, engine coolant system. So some of those I repeated this time around. Obviously, common faults we'd want to trap for. I identified some causes, identified some indicators. Some of them are the same: low oil pressure, low oil level. The sensors that we would need to identify some of these. And then we've got something new on the bottom here, and I'll zoom in just a tad. So now we've got some predictions in place based on the data that's being analyzed by those indicators, and I'll get back to that in a second. We are now able to make a prediction, or a couple of predictions. One prediction might be impending coolant system failure, and another one is an impending engine oil issue. And again, those issues could be related to low oil level, low oil pressure. This prediction has the ability to aggregate the input of multiple indicators to make it part of a prediction. So it's not just one indicator spurs off a prediction. It could, but more commonly, you might have some set of multiple indicators that are working together that then cause a prediction to happen. And again, I'll talk about the algorithms to make that happen in just a minute. First, I just want to mention the actions. So I've specified two actions, and the way I've got this set up this morning is each prediction actually spins off both actions. One action is actually a notification of the maintenance chief on the boat via email that one of these is happening. The other action is actually to spur off a deeper analytics application or algorithm that maybe we had previously written to do a deep root cause analysis on the last 7 days of data. So I point this out because some of these actions could be human-related actions: spur a notification, send a text message, send an email. or they could be computer-related actions. Send a data stream somewhere, run an additional analytics algorithm, spin off another application or system. So many different kinds of actions could happen. There's really no limit to it. So let me go out of our graph builder. I'll just show you briefly what we did for predictions and actions here. So predictions, you can see we have the two different kinds of predictions that are set up. The impending coolant system failure, which is based on these two indicators that I had specified earlier this morning. So those two indicators come together to spin up the prediction for coolant system failure. And I also had an oil issue prediction, which is based on two indicators that I had created for oil level and pressure. And remember, each of those indicators were connected to some sensors, okay, the way the whole system works end to end. And then what I did earlier today to specify the actions was use a UI similar, well, it was exactly this one, in fact. And what you do is you set the type of action. We've exposed a relatively small number of actions here, but really you're not at all limited to, it's very easy to add new action types into the system. The first couple here are related to sending, computer code messages into databases or other operational systems that you might already be running on the ship in this case. Some of these are related to sending notifications, email, SMS, and then you've got others that are pre-built integrations into service support and field service systems that you may be running in a local cloud or in a central cloud. And the interesting thing is here is these actions are not just simple text messages, John, please look at something. They can include in them embedded variables, which include all of the detailed information that a service tech or a head of operations or maintenance would need in order to understand what's actually going on. So you can embed these into the messages themselves by just pasting this text in. And then whoever receives this message, whether it's a human or another technical system, will know what data caused this problem, what indicator fired off, and hopefully what to do with it. So by now, going back to our graph, you've seen a pretty good end-to-end view, but there's one thing you might have thought is missing. Okay, it's great that the sensors are able to push data into some indicators, but how does the indicator know what to do with the data? How does it interpret the data? One thing I didn't show, I could have shown, but the sensor types themselves all have a little data schema associated with them. So we know how to turn this data into a common data format used in industrial systems. That's one thing. But you still have to tell the system, okay, how do we know if a low oil pressure is, what do we do if our oil level is too high or too low? Is that something we should care about? Okay. And so very quickly, I can do that in the indicator algorithm section. Now, this is the first time in this entire flow of creating this operational, system for machine monitoring and predictive maintenance and fault cause analysis, where you're probably going to want to bring in a data analyst or somebody who knows computer code. You could set up this entire system up to now, basically just the machine expert and the AI working together. But of course, we love our technical friends and we can't, and we want their help to actually finalize, especially the creation of the algorithms necessary to interpret and process the data coming off the sensors. But even in that case, we can get the AI to help us out a lot. Some of you on the technical side probably know something like 60% of all computer code now being written and checked into code repositories is written by AI today. So the idea of AI actually writing code is nothing new. So what if we were actually trying to write an algorithm for low oil level, right, using the float switch that I had identified when I built it this morning. And instead of writing that algorithm or that Python script is what this will be by hand, I'm going to let our AI assistant help us with this. So here's what I want our algorithm to do. I'll try dictating this. If float switch shows oil level less than 50 liters, set output value to 1.0 period. Between 50 and 100 liters, scale output value between 1 and 0. Yeah, let's give that a shot. And there is the actual Python algorithm or little code snippet that is necessary to output the data stream that I just created. And let's paste that in. And now we would basically want to repeat this process for every indicator we created, and have somebody who knows code come in, double check, make sure that it was appropriately written and really capturing. I didn't show, but you could iterate many times with the AI Copilot on getting this algorithm exactly right. This one, those that know code probably could potentially see some issues here already, but that's what we want to do, is collaborate back and forth and get this exactly right. And by doing this for each of the indicators that we identified here in our graph, we can tell it what to do, how to do some pre-processing of the data coming off these sensors, and therefore be able to intelligently spit off the predictions and the actions. From that point, you literally have all the foundation of a running application to monitor and maintain and predict your main propulsion system on your tanker if I was to actually finish building this out. Of course, what you need now to do is to deploy it. And a whole other element of what Pratexo does is enable, as Gartner says, the management and orchestration of applications to the industrial edge. That's really how Pratexo started, was enabling that kind of deployment and management of these systems. And so once you've created it with the expert system builder, like we just did in real time, you give it a name, tell it where to go. It packages it all up into a block of code, or a few different blocks of code that we then import into what we call the design studio. And then that could be deployed to your ship edge or your micro cloud running on the ship or whatever, or to a central cloud, or really anywhere you would want it to be deployed. I think that's it in a nutshell in terms of my demo. Again, feel free to be entering questions into the chat window, and I'm going to go back to the slides here and wrap it up. Okay, great. I love it when demos go well. So just to let you know, obviously this is all early days for these technologies. It's really revolutionary. I've been in the industrial, call it IoT space, for the last decade, and in my experience, to be able to actually build an application like you just saw could take a year, lot longer. And now that time has been reduced just incredibly. But by instead of having coders trying to figure out how a complex technical system should work, you have machine experts who really know those systems working with a very smart AI that can do all this. So we have a couple of pilots now in progress with this technology, which are really, really cool and very promising. We are looking for 2 more actual organizations to finish out the pilot phase of this new technology and get it into production. I call them pilots, but actually Pratexo doesn't really do pilots. We build production level systems, and so we want to use this technology to do exactly that. Little bit about Pratexo to wrap it up, and then we'll open it up to Q&A. So as I said, I think right at the beginning, we are focused on accelerating the ability to deploy and manage solutions such as this predictive maintenance expert system we just talked about, all the way from the far industrial maritime edge all up to central clouds, and really bring a lot of the benefits that we've been working on in cloud computing for really the last 20 years, bring them closer to the edge. As I said, there needs to be a balance between the far edge, the ship edge, the industrial edge, and central clouds. You obviously cannot push all data up to a central cloud for so many reasons. And probably you can't have every computing task is not suited to the edge either. There needs to be a balance, and we're focused on enabling that balance, and therefore unlocking now the power of AI and the ability to process data in real time and basically address critical operational issues, especially system resiliency, widely defined as a really critical aspect of what Pratexo solutions are all about. And as I said, resiliency, efficiency and uptime, improve system automation. And of course, we didn't discuss it, but one of the actions that could be spread out, of course, is to automatically shut a machine down if the engine gets too hot, or take other kind of automatic machine control type action, as well as we increasingly move to automate these systems. and great benefits, including reducing operating costs, achieving emissions, carbon reduction targets are a big part of system efficiency and uptime, often use cases related to safety and security. And then sometimes these technologies open up new ways of actually generating revenue, increasing margin, because you're able to do things you just weren't able to do before. I think this is my last slide. So when I think of Pratexo as a company, we bring together our expertise and some of the technology you saw briefly in edge to cloud computing. The studio is the platform which actually enables the deployment of these systems, like the one we just built, that expert system, to the industrial edge. And then finally, the application layer, like the one we just built, you could consider it a sort of an enhanced condition monitoring and alerting system that's able to take action, all enabled by generative AI. Really critical. And our mandate and mission is to bring all these things together for industrial related applications. And that's it. Wow. So open to whatever questions we might have. There's the QR code again if you want to. I've got a few things there. The ABB review article about our original expert system project. I've got a video of an actual demo of the expert system like I gave you today. The demo in that case is one remote compact transformers in transformer substations. It's an electrification example, not a maritime example, but the video is there. And I believe Dr. Abili mentioned that you will have access to this recording and the slides as well. But of course, you can reach out to me at any point in time, and I'd be happy to talk to anyone in more detail. So let's see. Do we have any questions, Dr. Abili?
Yes, we do have some questions. Basically, the first question here, it says to capture data, should all components have sensors or just critical components or parts?
Well, yeah, great question. And of course, most more recent machines and industrial systems, whether they're on in maritime settings or not, are all starting to become replete with sensors, right? And in fact, that's one of the reasons, one of the drivers of edge computing is because more and more data is being pushed off these engines and switchgear and all the other systems that we've got. You just cannot possibly push it all gigabytes or terabytes of data a day into central clouds for processing, nor would you ever want to. So that's a big driver for edge computing in the first place. Now, when you're talking about legacy equipment, that's where you can be more creative, I think, in some ways, in terms of selecting the type of, third-party or OEM sensors that might be necessary. For example, if your legacy engine doesn't have a built-in sensor for temperature, you could easily mount a thermal sensor, right on the engine, or some other type of sensor that could detect temperature. I think the way to start with this, and it's important that this graph went in the order that it did, right, is we started, in fact, I'll pull the graph back up again because I think it's important to see. There's a reason we started with faults and then worked our way to sensors and not the other way around, right? Start with what are you trying to solve for, right? What are you trying to detect? Another angle might be actually to start at predictions. And the way our system works, I didn't show it, but you can actually start entering predictions right from the start. They will appear on the left side of the chart here. And then eventually, as you connect them into indicators, they move over to the right. But that's what I'd recommend. Start with the faults or start with what you want to predict, and then you work your way down to the sensors you need. Don't start with the sensors, So great question, by the way.
Yeah, good. So the second question here, how can generative AI help drive predictive maintenance and operational efficiency use cases in offshore marine operations?
Well, the cool thing about these kind of systems or these kind of collaborative tools is you're not limited to any particular type of context. Like I have a very wide scope. I talked about propulsion systems here, but I could talk about, automated docking. Well, if I could type systems, okay, automated docking systems. All right. Let's just see what spits out. I've never done this before, obviously. Probably should have reset the. Oh, okay. Look at that. It did work, even though I didn't clear the mind out. So if I was building an automated docking system for a port, these are some of the faults that I would look for: collisions, incorrect alignment. Yeah, all of these. Those are probably pretty obvious faults. And then what would the fault cause graph look like? So we are not, again, and remember, this is not the final fault cause graph. This is just the initial indication. Is my co-pilot thinking in the right direction? It appears like it is. Now we would have an expert in ship docking build out what that would actually look like. So these tools are very flexible by combining, the sort of inherent knowledge of a human expert. And we all know the stories of the person who opens the door to a machine and feels how warm it is, or can hear the sound and goes, oh, there's something wrong, right? How do we take that kind of expertise, as many of these experts are retiring and everything else, and build it into an expert system? That was the original thing we started with ABB, until we sort of hit the roadblock about how we turn that knowledge into an application. And as you can see, I just in real time just began the work on an automated docking system here, right? Which I don't know anything about, right? I could choose virtually any domain and work us through a decent building an actual application to monitor and maintain this system. Just began the work on automated. Other questions, Dr. Bailey?
Yes, we do have some more questions too. Yeah, so how can generative AI augment human performance in training less experienced resources to accelerate asset reliability and availability?
Well, good question. I hope I've already addressed some of that in terms of the presentation today, but it does remind me of one other important element here. Let me go to this fault cause graph here. So an important thing to keep in mind is, you notice one of my actions here is notifying, the maintenance chief of something, or notifying or sending a text message to the person on watch at that time that there's an impending coolant system failure. This is the magic here is not only about sending a notification that somebody sees, but it's about then helping that person go back to the root cause. So what caused this engine overheating problem that we just got, or this coolant system failure that we just got notified of? What caused this impending oil issue? So it's not only about predicting and notifying, but it's about, back to the basis of why we did this in the first place, root cause analysis, which will be very important for enabling a human service technician to be able to collaborate with the AI, really go back through the graph, understanding the root cause, and then know exactly what to do about it. So that's another element of this that we didn't really talk about too much.
Good. So more question again. The next question here: what are the potential risks the industry needs to be aware in deploying generative AI on asset operations?
Great question about potential risks of employing generative AI. Well, I'm sure we've all heard in the popular press about, AI hallucinating, which sort of making stuff up is, and just like people sometimes make stuff up, there's no surprise that intelligent AI engines sort of have the potential to do the same thing. This is exactly why, going back to our other example here, I had entered automated docking system, and it created an initial fault cause graph. What I would not do is just say, done, implement. Okay, deploy this graph, right? This is why what we're doing is deploy this application. What we're doing is enabling an intelligent collaboration between the human experts with an assist from generative AI. We're not allowing the AI to just go off and do it all on its own, because, of course, again, for the potential of errors, of not fully understanding the problem, or of just not really understanding the faults you care about. Like if you're building this docking system, you might really care about it, preventing collisions, incorrect alignment, but you're not concerned about power failures, for example, right? So this is all about enabling a human and intelligent machine collaboration, not just allowing the expert system or the generative AI to just go off on its own and do things. Great question. Anything else, Dr.?
Yes. Yeah. So can you explain the connection between resilience and AI?
Yeah, well, so I think that's a really good point. So there may be many goals that you have with building a system like this, and I sort of touched on it back here a little bit, right? You may be focused on reducing operating costs, enhancing the safety of your systems, like maybe the docking example I just gave could be mainly safe. That might be the main motivation for it is mainly safety oriented. But in my experience with industrial systems like this, a big motivator is often system resiliency. That's why I have this one at the top: system efficiency and uptime, right? You need your system always on, operating at peak efficiency. Of course, you need to be able to react quickly if something does happen by understanding the root cause of that problem. That's important, but even better, to prevent it from happening in the first place. And we all know in our own domains the stats on how expensive an hour of downtime is, or a day or a week of downtime is. Usually it's millions of dollars, right? So relative to the cost of rapidly designing and implementing a system like this, which is de minimis relative to the benefit of driving system resiliency. So that's a big lens I use for this. I gave a presentation at Distributech a couple of weeks ago on this concept of resiliency in energy systems. And whether it's an energy system or a maritime system or a manufacturing operation, the concepts are very similar.
All right, good. Thank you. The next question, is this technology deployed at the edge, or is this something that can be deployed at the enterprise level? That is level 1, 2, versus level 4 and 5.
Yeah, great question. In fact, we didn't go into this in detail in the presentation today, but the notion here is that you can deploy these kind of applications or systems like the one we literally just built all the way at the far edge, for example, on edge computers running on a ship, or maybe on what we call a micro cloud. It's a little resilient cluster of computing resource running on the ship, connected to the sensors and systems. That's what probably would happen in the example we just gave. But you could have multiple tiers of this. You could have a fleet of ships connected together into a regional application that's understanding overall efficiency across that fleet. And then, of course, you could have some elements that are living in central clouds, so that span an entire enterprise or organization. And again, we didn't talk about it in much detail today, but you could deploy these applications like the one we just built, on a little industrial PC running on a DIN rail in a ship, all the way up to a massive central corporate cloud, either on premises or maybe an on-premises secure cloud, or maybe one of the hyperscaler clouds. So it's quite easy to decide where you want to deploy these systems depending on what you're actually trying to achieve.
Good. Yeah, one more question. How can generative AI be deployed in electrifying assets, performance use cases?
Yeah, great question. And as I mentioned a couple of weeks ago at Distributech, that was my theme. That was the demo I was giving. And if you click that QR code that I showed you earlier, it'll actually take you to a specific example of applying this technology in the electrification domain. Part of the additional challenge you have there is these systems tend to be highly distributed, decentralized in nature. For example, in the Norwegian power grid, we're running Pratexo today across dozens of remote transformer stations, soon to be hundreds of these stations, all collecting massive amounts of data, processing most of it locally, because you couldn't possibly send it all up to a central cloud, and then enabling, predicting and preventing issues from happening. So the energy transition that's going on right now toward electrification is huge, and we know it's impacting the maritime industry as well. And we definitely see that as a big driver of solutions like Pratexo.
Okay, good. So one more question. Can this technology actually help address ESG?
Yeah, exactly right. So decarbonization, ESG more broadly is a critical driver. And in fact, our mission statement as a company is to help drive the energy transition and the decarbonization of the world. So the way we do that is by implementing systems quickly that affect system efficiency, uptime, resiliency, all the things we talked about earlier. But one of the key fundamental goals of these technologies, I think, is they will absolutely be necessary to achieve our targets, which we're already in serious danger of missing. So we have to move more quickly. I know the industries that Pratexo works in, energy and in infrastructure, maritime, are conservative industries by nature. It's understood why that is necessary. At the same time, we have to be able to adopt these kind of technologies more rapidly if we have any hope of achieving our targets, whether it's our targets for global emissions on the maritime sense or any of the other industries we work in. So, we're really focused on helping you do exactly that.
Good. So is there any internet audience for this reliability, maintenance, engineering, IT, OT at corporate level? Is there any target audience?
We developed the Pratexo platform as industry agnostic, you might say. And as you can tell, even from the examples I put into the expert system, I could have put in docking systems, ship propulsion, substations. I could have put in manufacturing performance in an MDF production plant. So the technology is not limited to any one particular industry. We do have an initial early focus on the energy industry. They do tend to be distributed, decentralized systems, lots of data. And as I mentioned a while ago, winning the ABB Startup Challenge, out of over 100 startups in 2022 auditioned for that. We won it. Helped further push us an early focus, you might say, in the energy or electrification space. But as I'm sure you all know, ABB is a huge supplier into maritime as well. So we're very excited about the possibility of opening our technology up to the audience here. And again, specifically to the expert system, we're looking for a couple of additional projects to collaborate with you on. If you're interested, reach out to me.
Good. So one final question: can AI co-pilots, save huge amount of time and resources in driving value outcomes on asset intelligence?
Yeah. Well, any of you that have been involved in trying to build or deploy these kind of systems, like the one I showed you for predictive maintenance and system analytics, knows this is a non-trivial thing, right? These projects can take months, often years to implement. And so a big focus of Pratexo generally, and certainly the expert system builder, is to dramatically reduce that time, right? You still need to test, you need to do the physical deployment. It's not like this can all be done in a few hours, but to have something running in the real world instead of months or years, and maybe it's weeks or months, that's a dramatic cost saving. It's dramatic acceleration of the work you're already doing. And probably you're going to do this one of two ways otherwise. You're going to build something from scratch, which is slow and risky, or you're going to try to take an off-the-shelf solution and then spend the next 2 years either customizing it to fit your needs or changing the way you operate to fit how the application works. With a system like we've just shown, you can have the best of both worlds. You can very quickly create an absolute custom system. It's exactly the one you need. So anyway, happy to talk to you more about that. And I appreciate all the great questions. These are really good.
Yeah, thank you so much, Blaine, for answering these questions. They've been very helpful to the audience today. So we want to thank our global viewers who were able to join us in this webinar for the questions provided. We greatly thank our speaker, Blaine Mathieu, for the well-delivered presentation and, of course, putting some more insight into the questions, provided by our delegates. The IMarEST do offer CBD to viewers attending this webinar. So if you do attend this webinar, I do expect a CBD to be sent to you via emails, just like the way you receive the links on the emails. This is how we're going to bring our webinar to an end. We thank you all for joining us. We look forward to having you in our future webinars. Do have a great day.
Thank you. Bye-bye.